Procedural statements are very similar to the statements we have in high level language like C, C++. For example, we have this if and else statements. In case of if and else, we have, for example, we can write if, and after that we can have a logical expression. So based on the result of logical expression, we can assign the output, or assign, we can have any kind of a statement here. So this statement could be a logic expression, or it could be any behavioral expression. Okay, but the important point here is that in the parenthesis there would be a logical expression. So logical expression means it would be either conditional statement, less than, equal to, or more than, or it would be logical and, logical or, those kind of statements. So for example, this statement means if enable is 1, then out would be assigned as in. Okay, so because we are using if statement, and because we are using this equal to sign, now this will become a blocking statement. So this is a blocking statement. After that, if we are using next if, then this will also be a blocking statement. So in this type of if, like even though there is no else, then also it will work. Now, the other possible example is, let's say we have more than one statement which we would write or like to write in this if block. So in that case, for example, here we are saying number q is less than depth. So this is a logic expression. If this expression is true, then for binding multiple statements or multiple expressions, multiple statements, then we have to use begin and else, begin and end. So in C, C++, we use curly braces, start curly brace and end curly brace. Here we are using begin and end. Nothing else is different. So otherwise the syntax is very similar to C syntax. Okay, the other thing which you can also see, for example, here we are saying number q is equal to number q plus 1. So that means we don't have that incrementer operand here. That urinary operator is not there, so that's why we have to write explicitly that number q is equal to number q plus 1. Now let's say if we would like to have if as well as else, so either it could be nested or it could be non-nested one. So in case it is nested, then we can write if, then the expression, then the statement corresponding to that, then else. After that we again have to write if. You can see this particular syntax is also is quite similar to the syntax of C or C++. The only difference is that if we have multiple statement in this if block, then we'll use begin and end. Otherwise, there is not much of the difference. In the end of this logical if else ladder, so we can end the ladder by else. Okay, so another comment here, that this if else ladder or if else case, you can also see that it's also very similar to priority. If you're designing something like priority encoder, because this if is going to have highest priority. If this condition is not true, then only you are going to the else condition, and then you are checking for the next logic comparison. Okay, so using this if else if statements, then we can also create something like if we had to design something of priority conditions. Okay, then that can be designed using if else statements. So these are about if else conditions, and sometimes we would also like to have multiple wave branches. So in multiple wave branches, we can use case statements. Case statements are also similar to our C statement. So we have to write case and then the variable which is controlling. So whatever is the variable name we are writing, so then there would be case items. So these case items would compare the value of control or value of this variable and compare with all the values, and then we will keep on then we'll write the statements corresponding to that particular comparison. So for example, here we are saying case ALU control. ALU control is a variable which is deciding our switch case. Now, if the value of ALU control, which is a 2-bit signal here, so if the value is 0 0, then we are saying y equal to x plus y. If the value of this control signal is 0 1, then y equal to x minus y, and then 1 0 y equal to x plus 1. If it is 1 1, then we are saying y equal to y plus 1. So these statements could be anything. And again, if we would like to have multiple statements, then we have to use begin and end. Okay, so now you can also ask this thing that if it's a 2-bit control, if ALU control is only a 2-bit variable, then if we have covered all the cases 0 0 0 1 1 0 1 1, then should we write a default here or not? So default means when any of these cases is not matched, then what should be where should we go, or what should we do? So in that case, it looks like here that there is no default statement required, but default statement is required or essential because of the type of variables we have. So you see, in case of Verilog, any particular bit or any particular wire can take 4 values: 0, 1, x, and z. So if the value of ALU control is, let's say, xx, or basically unknown, then what should be the output? It should depend on the default case. And when all the case items are done, then we have to write end case so that we can switch or basically close this case block. Okay, so the case block can be utilized to design multiplexers. So for example, this is a kind of a multiplexer where we are deciding based on the control, we are deciding what would be the output. So yeah, so this we have already discussed, that if there are multiple statements, we have to use begin and end for that particular item. And default also we have understood, we have seen that because there is a possibility of x and z. Now one more thing here, that so there is some more advanced case statements is called case x and case z. So in case of case x, what sometime, for example, we would like to have a don't care condition. So let's consider this case itself. So we would like to have, let's say, 3-bit control. In third bit, we are saying that if either it is 0 0 0 or 0 0 1, then we have to perform this operation. Then instead of writing both the case items, we can write 0 0 x and then y equal to x plus y. So which means that now the third bit is taken as a don't care. So in case of case z, wherever we would like to take don't care, we can write z there, and wherever we like to have a don't care in, then we can write x in the case of case x. So this case x and case z could also be used if we have a larger cases, and some of the case items can be combined because some particular bits are don't care there. Okay, so this case is also a good mechanism to essentially implement multiplexers or demultiplexers. Now, the other set of statements in procedural procedures are like loops. So there could be multiple type of loops. While loops. In case of while loop, we write a condition, we initialize, and after that we say that this loop will keep on running until this condition is true. So for example, here we are saying while count is less than 128, then we will keep on running this procedure. If count is 0, so that means we have to initialize it to 0, and after that we can have this while and then expression, logical expression. Until this logical expression is 1, you will keep on rotating in this loop. Again, if there is only single statement, begin and end is not, this begin and this end is not required. But if the number of statements are more than 1, then we have to use a begin and end. So here we are saying count equal to count plus 1, and then we are displaying. So similar to while loop, there can also be a for loop. The for loop syntax is exactly same as the syntax in C. So you can write for and then initialization part, and after that your logical expression, and then you can have the increment part also, decrement part also. The only thing is urinary operator is not there in Verilog, so you have to write count equal to count plus 1 or something similar. Because there is only single statement, so I'm not using begin and end. I can write the single statement as the way it is. Okay, so similar to while loop and for loop, there could be a repeat loop here. So in repeat loop, we know the constant number of times when we are going to repeat a particular loop. So we can now in the same thing, the same example we are writing in terms of a repeat loop. So here we are specifying like a constant that how many times we would like to repeat this loop. You can say repeat and that number or how many times we would like to have this particular block repeated. Then we can have begin and then the list of statements which we would like to get repeated. Similar to repeat loop, there is another one which is called forever loop. So in forever loop, we can there is so this value of repeat is essentially infinite. It will keep on running. For generating signals like clock, this could be used. For example, we can say it could be written in initial block clock. We are initializing some value, and then we can say forever, every time, or this will keep on executing that after 10 units of time, clock is equal to not clock. Now, again, you will say that does this forever means that it will keep on executing? Actually, yes. But what will stop? So let's say if you are writing anywhere in your test bench or anywhere in your design, that what is the condition you would like to do a dollar finish. So if you specify that after so many number of cycles I would like to do dollar finish, then the execution or simulation can finish. Other thing is you can also have some sort of a logical expression and say that when this particular logical expression would happen, then you can assign a dollar finish. So that means your conditions. So for example, you can have a some application. Let's say you're doing sorting. So whenever this sort will finish, then you can generate a signal and you say that when the signal is 1, then I will do a dollar finish or I'll finish my simulation. So here for simplicity, because we don't know how many times or what should be the number of cycles it will take, so we are writing for simplicity forever, but in some other block we are writing a dollar finish according to when my simulation should finish. So these were the major or important procedural statements. There is also possibility to create functions in Verilog, but for sake of simplicity, I'm not covering that. And the kind of assignments or kind of Verilog program we are going to write in this course, they would not be required. These statements would be more than sufficient to design most of the logic. Okay, so if you want to explore more, you can go into tutorials and read books and see that what could be the other statements which you can use. But more or less, whatever statements we have covered, they should be sufficient in most of the scenarios. Okay, so now let's take a couple of examples at how we can use behavior modeling. So we have already seen a multiplexer to certain extent, but let's do it again. So now I would like to model a multiplexer using behavior model. In case I would wanted to model a multiplexer in structural model, then I'll start with and or, and then I list all the logic where it has to be ANDed and or in case of in case of data flow modeling also, I'll find out all the conditions, then my out would be 1. But here we can write it using a case statement. My modules definition would be similar to any data flow model or a structural model. I'll specify that what is my output, what are my inputs. Then I have to specify my ports, that out is a output port, and I0, I1, I2, I3, S0 and S1 are the select inputs. So all of these are the input. Now, because we are planning to use behavior model, and we know we are going to write onto out, so we have to specifically specify that this out is actually a register or reg type. Although we have defined it as output, but in addition to that we have also specified that this out is of type reg. So if we don't specify, then it would be assumed as a wire, which it is not, because we are going to write it in a procedural statement. So we have defined out as a reg type, and then we have to define an always block. And in the always block, we can write a case statement. So in the case statement, we are concatenating S0 and S1. So we are using this parenthesis operator, which is a catenation operator. Now S0 and S1 both together is one variable against which we are checking all the values. It's a 2-bit variable. It become a 2-bit variable. So if that 2-bit value is 0 0, then we are saying out equal to I0. If 2-bit value is 0 1, we are saying out equal to I1. Similarly, when 2-bit value is 1 0, then we are saying out equal to I2. And when 2-bit value is 1 1, we are saying out equal to I3. And when it is none of them, then we have to say that because we are not, so that means, what does it mean? It means either of S1 and S0 is X or Z, because my control input to my select input to my multiplexer is not known. So that's why we have to, it's good to say that out is equal to unknown. So out is also unknown if we our select is unknown. Now the question, when should it get triggered? We would like to get this particular block triggered whenever there is a change in S0, whenever there is a change in S1, or whenever there is a change in I0, I1, I2 and I3. So for example, S0 and S1 is not changing, but I0 gets changed. So there is a possibility that S1 and S0 value was 0 0, and whatever is the value of I0, that should be given to output. So that's why my sensitivity list, or the list of variables when it will get triggered, should be all S1, S0, I0, I1, I2, I3. So these are all right hand side variables, and in short, we can also write at the rate, parenthesis and asterisk. So this asterisk or wildcard means that all the variables which we are going to read would be in this sensitivity list. So when any of these variables will get changed, then we are again triggering this particular always block. So this is how we can model multiplexer. The next example could be the D flip-flop. So it's an example of a sequential logic. So uh, before going to D flip-flop, let's start with the D latch. Latch means it's a level sensitive, and in addition, we are also saying it is asynchronous. So my my gated value here is clock, and a reset is my asynchronous. So what I can do is I can write at always at the rate reset clock or D. So whenever there is a change in reset, whenever there is a change in clock, and whenever there is a change in D, this block should get triggered. So what does asynchronous reset means? That whenever, so this has the highest priority. So whenever a reset is 1, whenever reset is 1, we have to say that Q, my output, is going to be 0. So we also have to remember that because we are writing Q, this Q should be of reg type. So whenever reset is 1, then output Q would be equal to 0. So remember that if there is no change in the reset, then only we will go to the next block, means else of this if statement. But if there is a change in reset and reset is equal to 1, then we are not even going to the next any of the next statement. So this is how priority will get decided, and that's how we have to write, and that's how here reset has got higher priority than a D or clock. So if reset is 0, so that means then now we have to see whether clock is 1. Clock is a gated signal here. If clock is 1, then Q equal to D. If clock is 0 or my gated signal is 0, that means my Q is going to remain as the previous value. Okay, so in summary, we are able to write behavior of my delatch. We can summarize our delatch behavior that if reset is 1, then we are saying my output is 0. In case reset is 0, then we are checking about clock. If clock is 1, then Q is equal to D. If clock is 0, then Q is actually the previous one, which we are not writing here, but it is implicit. Okay, so now let's say we would like to have an edge triggered flip-flop. So the major change would be there in the edge triggered flip-flop is in the list of events we have to write positive edge or negative edge of the clock. So when let's say we are writing positive edge of the clock, because we have asynchronous reset. So let's say the reset is level low is active low. So if it is active low, then we have to write negative edge of the reset. Why we are writing negative edge of the reset? Because whenever negative edge is there, then only the possibility of reset being 0 would be there. Okay, so if there is a negative edge of the reset or there is a positive edge of the clock, then this always block will get triggered. So again, because reset is asynchronous, and that means it has higher priority. So if reset is 0, then we are saying Q equal to 0 or output is equal to 0. Else we are saying Q equal to D. So you see, we are not writing if clock, because positive edge of the clock will make sure that my clock is at this positive edge transition, and it would be 1 when this this D value would be taken before the positive edge, and it would be assigned to Q, and Q will remain there for 1 clock period. So this is how we can design a D flip-flop or model a D flip-flop. And because we are writing this always block at the rate post clock edge and negative reset, etc. So synthesis tool has is able to will be able to identify this kind of a syntax, and it would be able to act accordingly whenever this kind of a syntax is there. So sort of pattern matching would happen, and this would be synthesized as a flip-flop in case of a hardware synthesis also. So let's say we would like to design a counter. So this is another example. So now again I am writing complete module. So module the counter module will have 3 inputs, two inputs and 1 output. Output is Q. Let's say it is a 4-bit counter. So and there would be another input clock and another input is clear. So the functionality, let's say, is that whenever clear is there, then counter will start at 0, and otherwise at every clock it will keep on incrementing. What would happen if a 4-bit value of Q is 1 1 1 1? Then the next value will become 0 0 0 0. So that's the overall behavior of counter. So first we have to define the module, and then we have to say the output is equal to output is Q, and we are defining input also. And because here during the definition of the module we are not specifying how many bits, but when we are specifying output port or input port, then we explicitly say how many bits are there in the output or input. Now since Q is the output, and because it is being also written in an always block, so we have to define it as a reg type. Okay, so again, let's say that this particular block is this particular counter will get triggered whenever there is a negative edge of the clock, or and my clear is actually active high. So because my clear is active high, so I can say always at the rate post edge, because after post edge there would be clear would be 1. So when we are saying so, then we can say that because if clear is 1, then I need not to think about clock. So I can say if clear is there, and clear can be there only if there is a passage. So only at that particular point of time I will trigger this clear thing, and if clear is there after positive edge, then I can assign my output Q to 0. So you remember this syntax that we are saying my Q is 4-bit, but here the specification here, or basically representation here, is decimal type. So we are not writing in binary, we are not writing in hexadecimal, but we are writing in decimal. Now in the else case, because there is no posage of clears, the only other condition left is negative edge of the clock. So at every negative edge of the clock, I am just going to say Q equal to Q plus 1. Now you'll see here that I have used non-blocking statements here, non-blocking assignments. So usually non-blocking assignments are usually preferred in case of flip-flop or flip-flop like structures, and they're also preferred whenever we are trying to model a data flow, or a combinational logic. Okay, so this whole procedure will be able to will be able to count whenever there is a negative edge of the clock. Okay, so we can end the module by end module. This yeah, okay. So this is how we can use this behavior modeling, and now we can summarize our lecture. So we have seen behavior modeling in this lecture, and we have also seen it's quite more powerful. Maybe one question may be arising in your mind that why we were not taught about this behavior modeling when we were talking initially about Verilog. So and why it was not recommended, or when it is recommended. So essentially this behavior model can be used for data flow modeling. Oh, sorry, this behavior model can be used for combinational logic, for sequential logic, as well as for test benches. But we have not preferred, or we have not taught it the behavior model to this particular assignment, because um, it would be more efficient, it would be more appropriate to use behavior model whenever we are modeling sequential circuits. When we are using sequential circuits, we don't have alternative, we have to use behavior model, because to implement D flip-flop or any kind of a memory structure, behavior models are most appropriate ones, because you have this reg type which is internally defined. This reg type essentially can hold two different values. One is the current value, another could be the future value, while wire cannot have two different values, so the previous value will get erased. So that's why it is usually good to have a behavior whenever we are using sequential, whenever we are modeling sequential circuits. It's good to use behavior model. For combinational logic also we can use behavior model, but during synthesis we are not sure what we are doing. And another biggest catch is that whenever we are using behavior model, we tend to write like a C program. However, if you are modeling a hardware, we have to visualize, or we have to write on paper that what my hardware module is going to be, what kind of operations will be there, how many cycles it will take, etc. So all of those things can be done if we are if we are using either combinational, either if we are using structural model or data flow model. When we are using behavior model, we tend to skip those details and we tend to write in a like a C programming way. The other disadvantage of using behavior model without thinking much is sometimes some of the construct is not synthesizable. So finally, when we are going to design a circuit or when we are going to synthesize it on FPGA, etc. So in those cases, it may not give the desirable result. We may be expecting, for example, a multiplexer, but it may be designing something else. So the cost may be different because we are leaving it to our synthesis tool that what to infer. Okay, so I would suggest to use judicially that when should we use behavioral statements, when do we use data flow and structural statements. The ideal thing would be to use mix of them. So sometime we can use behavior statements, and so for example, for designing flip flop, you don't have options. You have to write behavior statements, but we can design some basic modules and then connect those modules again using structural model, and where where all the assignments required to be continuous, then we can use data flow assignments. Okay, so this is about different kind of statements, different kind of modeling styles. So if you require any more help in your assignments while doing, and maybe some more constructs or maybe confusion in some constructs, so any of these links could be a very helpful mean. SC Word has a very good, nice explaining method, and they also give a lot of examples, and tutorial point as well as Java points also have list of topics. Uh, Mostly what I have observed during my experience that books may not be a very good idea, but these online methods, because the languages like VHDL, Verilog, they're quite extensive, and there could be quite small scenarios or corner cases which may not be covered in the book, but these tutorials can help you quite a lot whenever you're dealing with any particular point. So with this, I would close this today's lecture. Thank you very much.